the final thing I wanted to bring up from this was this is the repo,
Yeah.
organic repo,
Okay.
Biopunk-Bioreactor. So
Yeah, yeah, and you can see the manuscript. So there's a couple folders there with manuscript and slides and posters. So if you go to the PDF there, obviously, like I don't hide the fact this is AI generated, but
yeah,
again, I have a lot of not guardrails on it, but I put in a lot of effort into making these really information rich. um, and yeah, so it's both a comparison of bioreactors as well as a critique of the Open Evo paper, which ends. If you go to the slides as opposed to the poster,
okay, right
I
there.
think the slides are a bit better
Yeah,
in terms of yeah. So the the benefits of these, what they're used for in terms of kind of the roles of this equipment in a particular lab, um, and yeah, and then some of our kind of like assessment of the pros and cons of each. And as you yeah as you go down, you'll see more about just the what were some of the history of these in terms of how they kind of what they came from in terms of the chemostats. You can see there, those are the seminal papers for, I think it's the Novick papers, and of course Minot.
yeah,
um uh, uh but that would be like 48, and I think the Novick's like 50. um but again, it's like they have a long history. There was a bunch of papers, kind of like 20. I mean, certainly, again, long history. um
right.
but the like 2018 to 2022, there was just a bunch of papers where they were really being used for experiments as well as being demonstrated as a kind of open source hardware technology. So you've got both like people coming out with this really inexpensive and accessible tool, as well as people demonstrating something very cool with it, um, or building on top of it, which is again the nice thing to see is like when another group takes that and then uses it to do some real science. So that's yeah. And so then I just try and go through some of the particular technologies of it, and we make some recommendations. You have to hit the more pages at the bottom there
Oh,
to see
yeah,
the more slides. Yeah. But so there's some just trying to point out what is missing from it, and kind of like how we can put together something which again is like kind of leveraging the best of each project, um, to make something that again is like an accessible tool that allows you to do frontier science.
yeah. I like this, and then I like your kind of distinction here: proto, devo, and bior. Bioreactor, the evolution, and the proto, sort of the characterization.
Yeah,
Um,
the Devo is confusing because, of course, it makes me think of Dev, but it's, of
development.
course, it's
Yeah.
directed evolution. Yeah,
Okay. Yeah.
it's
Yeah.
yeah,
So
yeah.
this seems to be a bottleneck in terms of automation. So I know like it takes, depending on your organism, it's going to take a while to do, and of course you need to have very precise be able to apply the same transfer techniques generation after generation, which is of course something that automation would be good at. But on the other hand, getting the data out and recording it at every generation, is that a problem in terms of automation, or is it just that no one's really done that yet?
It's you know, their point is it's easy. Their point is how to sample the system
Okay.
accurately while it's still cooking, so to speak,
Yeah,
right?
yeah.
And
Right.
and and you know, so like you'll see in this, it's got there's um, I mean, one of the biggest problems that we have is, of course, contamination,
Right.
and you know, getting so any time you can have a closed system that you know precludes those kinds of issues is a benefit, right?
Yeah.
The problem becomes how to also really sample the system, and you know, so again, there's some small discussion around, you know, how light has typically been used to kind of assess the system. Obviously, you'd like to do more than that. um, um, you'll see, you know, in the kind of like what's the proposal, the hardware proposal, you'll see, you know, some more there's some ways in which you can actually use CRISPR to get information about the system. Um, uh, so that's the problem of kind of like making it truly closed loop. Um, you know, where you're able to, you know, um, update it, and one of the things that they also point out is that what you kind of want to do is to also archive particular time points so that you can then do comparisons. So you kind of want to be able to take some of microbes at a particular point in evolution and biobank them, and then use them later to test against, you know, a much later version,
Right.
and then be able to use some sort of metrics in terms of like now these are different, and we see these differences because of these mutations or because of these genetic changes, and we see, you know, these metrics change, right?
Right.
So anyway, it's all covered in the paper.
Yeah.
Or
So yeah.
it's all covered in the write up, if you will. um, and uh, it does seem to be something that is certainly out of scope with some of the kind of more inexpensive educational projects.
Right.
Um, whether we can add that without adding significant cost is the question, which you know is super interesting if we can do that. Um, uh, so yeah. Anyway,
Yeah.
that's it's an open repo. I would love to, you know, I haven't. This was like pretty much just yesterday working on
Okay.
this,
Yeah.
and so but I was going to reach out to the Chai Bio guy, because the Chai Bio guy is the guy on Twitter who had got in touch with the Open Evo guy to say like, hey, what do you know, there is an open source tool. It's been around since 2020.
Yeah.
Um, uh, but I'd love to reach out to them. We use the Bioreactor project in the cores.
Okay.
Um, and then some of these others, you know, look like they're cool projects, but like their repos haven't been touched in, you know, many years. Um,
Right.
but they've still got a couple. They've still got a couple of interesting things that it's like still worth discussing them as for the yeah, design ideas that they have. Yeah.
Yeah, so that's good. Yeah, I just wanted to point out that the LTE, this is where your point about archiving different strains at different generations is actually been quite fruitful in this project because they do
Yeah.
archive,
Yeah.
at different generations, and then you can recall that generation, unfreeze it, and grow up that strain, and then you can make
Yeah.
comparisons. So, if I freeze something at 30,000 generations, and then at 50,000 generations, I want to go back and compare to see maybe
Yeah.
something has evolved in the genome or some,
Exactly.
they behave differently on a certain medium. Then you can do
Yeah.
that. And it just makes it more
Yeah.
flexible. Yeah.
Yeah. And I love thinking about this, right? I mean, it's as an undergrad, um, as a bio undergrad, I kind of learned a lot about this mathematically,
Right.
theoretically. Um, and what's really, part of this comes from being around a bunch of founders who care about biomanufacturing. So it's just interesting both to learn about how you can actually do this experimentally to recover all the theoretical results, as well as like what doesn't work, or like the actual pitfalls of this, and kind of yeah, like what you uh um, yeah, just the pitfalls of it, and problems that actually happen, and like you mentioned, I wouldn't have thought about archiving. um, uh, there's a number of things that I bring up in the paper that came from researching this that look like important concepts to understand for doing this kind of work. But again, really interested in how to make uh, a CRISPR accessible research platform that we can kind of like use, um, microbiology to do experiments.
Yeah, that's great. Well, thank you, Morgan. I want to finish up with a few things.